Yeah, solve this question: x plus y dx plus x and then x the y. Okay, so if you look at this question, it's differential is the exact differential equation format. And you can say this one. So this is a standard form for differential equation exact. Okay, let's now see if this equation is exact or not. Okay, since we take this form, then we can take this process as follows. Um, your m partial differential of m respect to no. I told previous video I've said that once you know your m, you have to determine which one is your m and which one is your n. Okay, and once you know your m, you do the partial differential respect to y, respect to the other function. And that will give us this is our m, which is the one that will have the x. The attachment to that is your m. Okay, and that differentiate this respect to y. That's one. Then your n partial differential of that respect to x, the one that has the attachment of the y, that's your n. And if you do the differentiation respect to y partially, you have respect to this respect to x. That will be product rule. You differentiate this one and keep this one constant. That will be ln x, then plus. Now differentiate this and keep this constant. Okay. If you differentiate ln x, derivative of this is what? Is 1 over the function. Okay? So that will give you ln x plus what? Plus 1. So that's what we have for that one. So this is not exact. This one is not exact. It's not equal to each other. So that make it to be what? Unexact, not exact. Is that the end of the road? No. Okay, it's not exact. There is still process you can take to make the differential equation, to make this to be what? Let's call this one to be exact. So what are the processes? The process is step one, use this expression. Let's check. It's going to give us a function of one variable. What is we have a partial differential of m respect to y is 1. Partial differential of n respect to x is ln x plus 1. Okay, all over n. My n is here. Is my n, which is what? X ln x. If you open the bracket there, this 1 and this 1 will go. Then we have what? We have minus ln x over what? X ln x. So that will go, and that will give us 1 over x. That will give us minus 1 over x. So with this now, we can go with this to get the integrating factor. Why? Because it contains just one function. Okay? So then integral factor will now become e exponential function of what? Of the whole thing we have here. Okay? Which is what? Minus 1 over x dx. Okay? If it doesn't contain one functions, then you have to use the other one. Okay? So this is what we have here, and that will be equal to what? Exponential function minus ln x, which is equal to what? E ln x minus 1, and that's equal to what? 1 over x. Okay? So with that now, we now go to equation 1, multiply equation 1 times your integral factor, times your integral factor. Equation 1 eqn1 times your integral factor, which is the functions of one variable, functions of x. And that will give me, that will be 1 over x into brackets x plus y dx plus 1 over x into brackets x ln x dy equal to 0. So this will be equal to, yeah, multiply this one with this one. Okay, that will be 1 plus y over x dx, then plus this one times this one, that's ln x dy equal to 0. And then m, we know the m, partial differential of m respect to y. This is my m, and this is my n. Okay, repeat the process for exact. Okay, once you multiply by integrating factor, then repeat the process for exact differential. So that will be equal to respect to y. You only differentiate the y, and that's what 1 over x. This one is a constant, that will be 0. Then come back here, partial differential of n respect to x, that will be 1 over x. So it's what is exact. It's exact. It's exact. And actually, we might not need this process. Once you multiply with the integral factor, automatically it will be exact. Okay, we have just concluded that this and this equal to this after this line. Okay, but it's good. It doesn't take time. You can show that. Then, since it's exact now, we can get the solution. There is a function. There is a function f of x such that partial differential of f respect to x is m. Okay, it's m. Okay, and my m is what? I have my m. You have, this is now your equation. Now this is one that is exact. This is your equation. This is your equation. So I'm making reference to this line now, to this one here. So my m is what? 1 plus what? 1 plus y over x. So integrate that partially. So integrate that, and that will be equal to what? 1 plus this over this, then partial differential, then plus what? G of what? G of y. Okay? Yeah. From here, the integral of this will be equal to integral of 1 is x plus, you keep this one constant. This one is just like, you keep this one constant. You're only integrating with respect to x. So that's 1 over x, and that will be ln x and y. Just like you have a constant. So that constant will go out. Just like that will be 4 or 3, it will go outside. And then you will need to differentiate that function x. And integral of 1 over x is ln x plus what? Plus g prime of y. Okay, then differentiate this. Differentiate this with respect to y. Then we have partial differential of f respect to y, and that is this expression, this symbol, that's n. That's n. Okay, equal to, differentiate this. If you differentiate respect to y, this will be 0. Then plus respect to y, you just have ln x. You have the ln x. Okay, plus what? G prime of what? G prime of y. Then n as a function of x comma y, we have a value for that, which is a. That's ln x. So that's ln x equal to what? Equal to ln x plus g prime of y. So ln x and this will cancel. Then have g prime of y equal to what? Equal to 0. So equal to 0. Equal to 0. Then you can integrate this, and that will be equal to f. Now become f is now, this is your f, x plus y ln x plus g of y is just c1. And don't forget, f is what? F is c. So c minus c1 is c. So we just have this plus this equal to c is a solution. The solution of the problem is a solution of the given question. The solution of the given problem. So the solution of the given problem. Look at this question. Consider this the mu is equal to x and integrated factor. Okay, for that given differential equation, this is dx y equal to 0. So this really conform to the general procedure of this plus uh, this plus this, the y. This is the dx equal to 0. So if this is conform to that standard, then we just take the process. And the process is just, we've been told that it's not, we've been told that we have an integrating factor. And what that means is that if you have integrating factor, that means this expression is not exact. And then with the integrating factor, once you multiply with that given problem, it will be exact. Okay, so let's now multiply with that. Equation 1 times uh, times this. Equation 1 times multiplied by this. So that will be equal to this one, x3 plus xy dx, and plus x f of x dy equal to 0. So, and we have said that once you multiply with the integrating factor, this automatically will be what? It will be exact. This given, this now will be exact. Okay, once you multiply with the integrating factor, it will be exact. Okay, so let's just get a value for this and a value for this. This is your m. Once you see dx, the attachment to that is your m. Okay, once you see the y, the attachment to that is n, and the equation must be equal to 0. So, respect to y here, we're going to have this one with 0. We only do this one, which will be equal to x equal to, yeah, partial differential of m respect to y. That's that value. And here also, this one, partial differential of n respect to x. We use the product rule. We do 1. Okay. We can keep this one constant and differentiate this, which will be equal to what? F of x, and then plus. Now differentiate this. Okay, and that will be x into bracket what? F of x. Yeah. That will be f prime of x. You differentiate that and keep the x constants. And these two given expression is just, you can write it as this. You can put prime on the two of them. Yeah. If you do put prime, differentiate of this product will give you this. Okay, will give you this. And while we are doing that, it's more better that way, so that we can this expression we know is a product rule, and that's that. You can just do that, put prime there. Okay, then for this differentiation to go, then you have to what? Integrate both sides. Integrate both sides. Okay, and that will be equal to x over 2. Okay, plus c equal to this one. It will go there. Then you have this differentiation will cancel. Then you have f of x. Then with this now, we can divide both sides by what? By x. Then you have x over 2 plus c over this equal to f of x. So that's your f of. The only thing here you've been wondering, since you are integrating both sides, once we are here at this point, you are here, s equal to f of x plus f prime of x. And I said that this, you can write it this one as this. Okay, you can write it as this. The differential of this. Okay. Okay, then you integrate both sides. Okay, and once you integrate both sides, this differentiation, this prime will go. So we just have, I mean, your constant will be on the other side. That will be s2 over 2 plus c. The c will be here, equal to what? Equal to x of f of x. Okay, then divide both sides by what? By x, so that you can get your f of x. And that's that question.